Okay, uh, so today we are going to study the notion of universality and in general properties of 1D maps. So we are basically going to build this. First we are going to study qualitative universality and certain properties, and then we are going to study quantitative universality. Basically, Feigenbaum's analysis of universality in one-dimensional unimodal maps. By unimodal map, we mean that the map basically has one hump. This is a unimodal map. And we are going to slowly build up to appreciating something, a very celebrated approach in physics, renormalization group. The notion of the concept of the renormalization group approach. Okay, so it is useful to visit again the orbit diagram for our logistic map. So that we do on the next page. So I'm going to borrow the so this was the bifurcation diagram or the orbit diagram, you can say, for the logistic map. And well, we already had an algorithm how we sort of got this diagram. Basically, you start with an initial condition and then you iterate forward, and once the transient motion gets settled onto a stable attractor, this is what this diagram is capturing. So at 3.5 there's a seems like a period 4 attractor where this trajectory has settled down. It goes through a period doubling and you get a period 8 attractor over here, so on and so forth. So that's is essentially. So again, I'll mention the algorithm. How do we get such a map or the orbit diagram? Essentially, we start from R. We set R to be 3.5, and we start from an initial condition. Let's say x equals to half. We iterate for 500 steps forward, and then we iterate for, and this basically allows the trajectory to settle on this attractor. So what is shown in this figure is the attractor, where the final trajectory starting from say x equals to half after 500 iterates maps to. So once the trajectory is settled, we iterate for 1000 times and plot those points. we increase R slightly and go back to step 2. So this way we proceed in R in this direction, and we plot the trajectory on the stable attractor in the Y direction. So that's essentially happening, and if you look at it, you see a period 4 attractor. This is probably a period 3 window. This is the route for period doubling. It becomes the period doubles, it becomes an 8 period 8 cycle, period 16, so on and so forth till R infinity, and beyond R infinity is chaos, and we'll come to that more later. And in between, as we crank up R, we show windows of let's say period P attractors are interspersed between chaos, and we get all this pattern going towards R equals to 4. In between chaotic regions, we have windows where a period P, in this case a period 3 orbit, becomes stable, so on and so forth. So that essentially is the bifurcation diagram, or the orbit diagram for this particular map. So with that, armed with that technology, just reminding ourselves, so what really is happening? Our first result is that so interestingly, now let's look at the comparison for the orbit diagram of the logistic map and the sign map. Remember, both of them are unimodal and one-dimensional maps. So this is the orbit diagram for the sign map, namely and this is our friend, the logistic map. Note the remarkable similarity. I must say remarkable similarity in these two maps. The orbit diagram seems to be strikingly similar. So this is a universal property for unimodal one-dimensional maps, and we'll state the universal property in a following way. So the theorem goes as following. Consider all unimodal maps where fx satisfies fx f0 equals to f1 equals to 0. So Metropolis proved this result is due to Metropolis in 1973 and authors. They showed that as R is varied, the parameter R is varied, the order in which stable periodic solutions appear is independent of the unimodal map being iterated. And the periodic attractors occur in the same sequence that is called as the U sequence or the universal sequence. So I'll just state the universal sequence up to period 6. So up to period 6, the universal sequence is 1, 2, 2 into 2, that's period 4, then 6, 5, 3, period doubling of the period 3 orbit, 5, 6, 4, 6, 5, 6. So it doesn't matter the algebraic form of the function f. This is the order in which the stable periodic orbits will occur. First it will be a period 1, period 2, period 4. Over here we are omitting all the higher. We are not including our usual friends, period doubling 8, 16, because we are just considering a U sequence up to order, up to period 6, then 6, 5, 3, so on and so forth. So this is the universal sequence in which the periodic solutions of the periodic orbits occur. And this is going to be independent of the map. So this is basically the first universality result, the order in which these periodic orbits occur. A period 6 orbit would be always preceded by 1, 2, 4, and of course 8, 16, all those things we are not including. This is just the universal sequence up to period 6. So that's a qualitative universality in the sense, and we can see that from the remarkable similarity in the orbit diagrams or the bifurcation diagrams of the sign map and the logistic map. Such a bifurcation diagram with the remarkable similarity would occur for any unimodal function, independent of the algebraic details of that function. So that's certainly a very interesting result. What can we say more about the periodic orbit? So there is another result, not necessarily to do with stable orbits, but this is more to do with the either stable or unstable orbits, it doesn't matter. So for that, we first need to consider the following sequence. So consider the following sequence. Sequence 3, 5, 7, 2 into 3, 2 into 5, 2 into 7. So I'm taking all the odd numbers except 1. Then I multiply by 2 all odd numbers except 1. Then I multiply by 2 to the power of 2 all the odd numbers except 1. And then finally I tack on all the powers of 2. So this sequence is called as the Sarkowski sequence. And The theorem goes as following. For 1D maps, M on x minus to infinity. So this is for 1D continuous maps. If a periodic orbit occurs with period t for this particular map, then we have to find where does p is in this Sarkozy sequence. So let's say in the Sarkozy sequence, if L comes after P in the sequence, in the Sarkozy sequence, this implies the map also has a periodic orbit with period L. So in particular, period 3 orbit, as it occurs the first guy in the sequence, implies the existence of periodic orbits of all integers. Therefore, in the range where the period 3 window is there for the logistic map, namely, let's say this was the period 3 window. So in this range, for the period 3 window, I have periodic orbits of all possible integers. That's remarkable. Well, the other thing is that why we just have mapped this, because only the period 3 orbit is stable. So this has periodic orbits for all integers, all periods, integers as period, and of course they are unstable, because in this period 3 window I have only one stable attractor, which is the periodic 3 attractor, but all these periodic orbits are there. So this is a remarkable result. So this remarkable result is not limited to that. So in 1975, Lee and York showed that existence of period 3 orbit also implies the existence of an uncountable set of orbits that are not periodic. That is, they never settle on a periodic orbit. So, of course, let's say in a period 3 window, as our example, in this period 3 window, such unstable orbits do occur. Uh, but since the only stable attractor is the period 3 orbit, all these aperiodic trajectories are unstable. That is, once we start very close to this unstable trajectory, they'll settle on a period 3 attractor. So I am going to again perhaps insert the picture. Let's see. Yeah. So consider this period 3 window. Since it has only, we have only the period 3 orbit as the stable attractor, all these aperiodic trajectories are unstable. Starting very close to such a trajectory, one would settle on a period 3 attractor. So imagine you start very close to such an unstable aperiodic orbit, not exactly on the aperiodic orbit, but very close to that. Eventually you will end up on the period 3 attractor. And the reason why in our simulations also we can see that only this period 3 zoom zoom zoom, the period 3 attractor shows up, it is because that this aperiodic trajectory, the initial conditions leading to aperiodic trajectories are measure zero. So it's called as zero Lebesgue measure. That means there are in the language of probability, the probability of hitting one aperiodic trajectory in a period 3 window, for example, is 0. So almost all points would lead you to a period 3 window. And not only these unstable periodic trajectories, these aperiodic trajectories are unstable in the sense that in the neighborhood you will end up on a period 3 window. They also form a 0 measure set. That explains why in the simulations we do not see those trajectories, because they are measure 0. So yeah, I mean, this can be contrasted to what happens in the bifurcation diagram initially when you had R and you started with a unstable point and you had some sort of a period doubling. So this is an attracting period 1 orbit where all points except 0 and 1 are attracted to period 1, over here we have an uncountable set of such points uh, which are on this aperiodic trajectory. Still they are measure 0. So this was essentially an idea, properties of periodic orbits in one-dimensional maps, then certain universality results about one-dimensional unimodal maps, the U sequence, the Sarkovsky sequence, and in general what really happens in as we crank up R in these systems, we get these periodic windows. We've shown that periodic windows, at least periodic windows itself, has a lot of rich structure. They might have unstable periodic trajectories. They have other unstable periodic points, and in general they have also the other unstable periodic trajectories based upon the Sarkovsky sequence. Then we had a notion of stable periodic orbits according to the universal sequence for unimodal maps, which we saw through this remarkable pattern that occurs for the sign map and the logistic map. And so from the next lecture we are going to study a bit about the quantitative aspects of universality and the Feigenbaum's theory.